In this video, I will explain the quantum Fourier transform. Let's start with a simple example. Suppose we have a recording of a piano chord, and we would like to see the individual tones it is composed of. The Fourier transform allows us to decompose the sound into This means that the original recording must have been the A major chord. More formally, Fourier transform is a linear operator given by this definition. It is a map between an integrable function in time domain to a function in the frequency domain. Note that both input and output are complex-valued functions, but for simplicity, we will only be showing their magnitudes here. Taking f, a function of time, and applying the Fourier transform, we get f hat, a function of frequency. The peaks correspond to the frequencies which are present in the original signal. If we took the peak frequencies and played them together, we would get the original signal back. In practice, we are working with discrete samples of the signal, so we use the discrete Fourier transform instead. The input is now a vector of complex numbers, and the output is also a vector of complex numbers. We replace them in the definition and use a finite sum instead of the integral. The discrete Fourier transform can be seen as a transformation between the time basis and the frequency or Fourier basis. The discrete Fourier transform is usually written in a normalized form. Since we know it is a linear map, we can rewrite the transform as matrix multiplication. The Fourier matrix F of size n is a special kind of Vandermonde matrix. Omega here is the nth root of unity. Remember, we normalized the matrix. The discrete Fourier transform is, therefore, a unitary operator. Do you already see where this is going? Let's now finally move to the quantum Fourier transform. We start with the 2 by 2 Fourier matrix. Does it look familiar to you? It is, of course, the Hadamard matrix. The Hadamard actually performs the Fourier transform on the amplitudes of computational basis states. Note well that a single gate applied on a single qubit performs the transform on two amplitudes simultaneously. Now that we know how the unitary operator works, let's see what the quantum circuits look like. A single Hadamard performs the quantum Fourier transform on two amplitudes. The 2-qubit circuit is more complicated. The Urot gate rotates the phase of the qubit. It is sometimes called the phase shift gate. We use it here as a controlled gate to transfer the phase. Finally, we need to swap the output qubits, and the Fourier transform is finished. The 3-qubit circuit repeats the same structure and performs the transform on 8 amplitudes. The pattern continues. We see that if we can encode the input vector into n amplitudes, only the logarithm of n qubits are needed. The number of gates is quadratic, but this is still an exponential speedup compared to the classical Fourier transform. The best classical algorithm known, the fast Fourier transform, runs in n log n time. Finally, let's see an example of the quantum Fourier transform of n equals 16, with 4 qubits. Our input will be this vector repeating the same pattern 4 times. Let's now apply the quantum Fourier transform. We will get this superposition as the output. Given enough measurements, we would be able to obtain these frequencies uniformly. We can easily verify that the output is correct and the same as the classical Fourier transform. Let us try to shift the original sequence since the frequency did not change. There is no change in the output of the transform either. And this demonstration concludes our video. I hope you enjoyed it.